Hello everyone and welcome to today's webinar to celebrate the 175th anniversary of the formation of the Institution of Mechanical Engineers. My name is Paul Jackson. I've been involved in pressure systems in various roles throughout my career, but today I'm representing the Institution of Mechanical Engineers Pressure Systems Group Committee, which I chaired for a number of years before Paul Smith, who's the current chairman and unfortunately can't be here today, took over. The Pressure Systems Group is one of the divisions and groups that make up the committee structure of the IMechE. The group brings together key players from manufacturing, process industries, inspection, academia, trade bodies, and the regulator, the Health and Safety Executive, to discuss the latest advances and issues and enable networking among industry leaders and promote pressure systems to all engineering professionals and the wider public. Today's webinar will demonstrate how the UK has been a leader in pressure systems technology. Whilst it may seem a mature technology, we will demonstrate how the future still holds many exciting challenges. The presentation will take approximately 40 minutes. During this time, you will be muted, but can post a question by clicking on the large triangle at the top right of your screen and following the instructions. At the end of the presentation, we have a Q&A session to answer the questions that you have posted. Our speaker today is Professor David Nash, who is one of the longest serving Pressure Systems Group members, joining shortly after graduating. After spending several years with a vessel fabricator, Professor Nash joined the Department of Mechanical Engineering at Strathclyde University as a researcher, where he gained an MSc and PhD, working on design methods for vessel supports and local loadings. He has written over 120 papers and 6 books on pressure systems topics, including bolted joints, buckling, impact analysis, and broader applications of finite element design by analysis. Professor Nash is a fellow of both the Institution of Mechanical Engineers and the American Society of Mechanical Engineers, ASME. As well as his university roles, he chairs the British Standards Design Methods Committee for PD 5500, the UK Pressure Vessel Code. He's a past vice chair of the Pressure Systems Group and has held several senior roles, such as chairing the 13th International Conference on Pressure Vessel Technology in London and representing the UK on the European Pressure Equipment Research Council, EPIRC. I will now hand you over to Professor Nash for today's webinar.
Well, thank you, Paul. I hope that's coming through nice and clear to all delegates today. And thank you for your kind introduction. It's a privilege to give this special webinar on behalf of the Institution of Mechanical Engineers and the Pressure Systems Group in particular. And also it's a challenge to cover all the contributions that have happened over the last 175 years. And as such, I will be cognizance of all of those who have worked in pressure vessels, piping systems, materials and fabrication over the years, and will be try to recognize their contributions in the pressure system story. I'm also thankful to our 113th president, Professor John Spence, who presented the Royal Nichols Memorial Lecture at the 10th ICPBT conference in Vienna in 2003. Milestones in Pressure Vessel Technology. And in that, a paper was written by John Spence and myself, and it really has a deeper dive into what we're going to share today. I also want to say thanks to yourself, Paul, for introducing this, and to my colleague Simon Erland, who is the BSI consultant for pressure vessels, for your input in wise words too. And as an overview to this webinar, I want to really start to take our thinking back to the start of the Industrial Revolution. look at a period of expansion and uptake of technology, the development of standards, look at learning from failure, looking at assuring safety, and then point towards some of the exciting future challenges which the pressure systems community is well placed to make a significant contribution. Our story starts pre the Industrial Revolution with the work to harness the power of steam, with the early pioneers of steam, Savary, Newcomen, and Watt, who are credited with the steam engine and its improvements. And this enabled the advent of powered machinery and powered transportation in both the railways and shipping industries. Thomas Savary patented a steam-powered pump. It worked with no piston, simply raising steam in a boiler, admitting it to a vessel, thus displacing water, and once full, a tap was closed, allowing it to condense, create a partial vacuum, and atmospheric pressure then pushed the water up. Although it functioned successfully, it was highly inefficient and wasted a lot of heat. Also, the fabrication at the time was very rudimentary, and solder joints were really not capable of withstanding the high pressure. So these had limited pumping capacity, and therefore mines required a series of these in stages to pump from any significant depth. Thomas Newcomen, however, created the first real practical fuel-burning atmospheric engine to improve ways to pump out water from mines in Devon. The steam enters the cylindrical vessel on the right-hand side and is then condensed. And the resulting vacuum draws down the piston and works the beam engine, which rocks in a central fulcrum attached to a pump at the base of the mine. The steam cylinder is then refilled with water drawn into the pump cylinder and expelled into a pipe to the surface by the weight of the machinery. And this first successful engine of this type at the Connaughey Coal Works near Dudley in the West Midlands, it was the form of engine that became the leader in both the UK and mainland Europe for some 75 years until the advent of the Watt steam engine. James Watt, along with Matthew Boulton, realized that the contemporary designs wasted a great deal of energy by repeated cooling and heating of the cylinder. And Watt introduced a design enhancement, the separate condenser, which avoided this waste of energy and radically improved the power, efficiency, and cost effectiveness of steam engines. Eventually, he adapted his engine to produce rotary motion, greatly broadening its use beyond just pumping water. And these improvements allowed the steam engine to replace the water wheel and horses as the main sources of power for British industry, thereby freeing it from any geographical constraint and becoming one of the main drivers in the Industrial Revolution. Richard Trevisik, who's often an unsung hero, is the inventor and mining engineer who was an early pioneer of steam-powered road and rail transport. And his most significant contributions were the development of the first high-pressure steam engine and the first working railway steam locomotive. On Christmas Eve 1801, Trevisik's Puffin Devil locomotive carried 6 passengers, and it travelled up a hill in Camborne. And this was the world's first ever successful journey by a steam locomotive. The operating pressure was about 50 psi. He also built a stationary engine at Coal Brookdale in Shropshire with a boiler pressure of 145 psi. He built another steam-powered road vehicle in 1803 called the London Steam Carriage, which attracted much attention from the public and press when he drove it that year in London from Holborn to Paddington and back. In the same year, however, one of Trevisik's stationary pumping engines in use at Greenwich exploded and killed 4 men. Although Trevisik considered the explosion to be caused by a case of careless operation rather than design error, the incident was exploited relentlessly by Watt and Boulton, who were his competitors at the time and promoters of the low-pressure engine, who highlighted the perceived risks of using high-pressure steam. Robert Stevenson, our second president of the IMechE, with his father, George Stevenson, being our first president, developed a rocket and it was the first to bring together several innovations at the time to produce the most advanced locomotive of its day. It is the most famous example of an evolving design of locomotives by Stevenson that became the template for most steam engines in the following 150 years. Steam-powered transportation expanded to the shipping industry, to paddle steamers, with Jonathan Hull credited with the first practical experiments to use steam to propel a vessel, and Henry Bell's Comet outside Glasgow at Dumbarton was the first commercially successful steamboat service in Europe. Sir William Fairburn, the IMechE's third president, developed the Lancashire boiler, and he also conducted early research into metal fatigue and was the first to show that the highest stress in the wall of a cylinder occurs around a cylinder's diameter, and that the hoop stress was twice the longitudinal stress. He was one of the first to conduct systematic investigations of failures, and he founded the Manchester Steam Users Association, which became recognised for setting national standards for high-pressure steam boilers. He also recognised that there had to be a balance between experience and training, recognising that there should be theoretical and practical knowledge and strength of materials and other requirements. And he also suggested that there should be training developed not just for those educated people, but those practitioners. Basically, he was an early founder and pioneer of CPD. And there's Fairburns equation connecting the pressure to the material resistance or strength and its diameter and thickness. Over the next 40, 50 years or so, there's rapid expansion, indeed the growth of an industry. Boilers became the powerhouses of many industries using steam. There was international adoption in Europe, the Americas, and the wider British Empire at the time. This is coupled with developments in the electricity field. A number of contributors shown there made significant contributions to developing practical electrical power, powered by steam. And then, of course, pressure systems in general were adopted by many industries for chemicals manufacture, shipbuilding, mining and minerals, for water and food production. And there saw rapid development in how the coal industry and the heating and power generation industries developed through lots of different technologies, including water-cooled furnaces, pulverizing mills, drums, economizers and superheaters, and so on. And one of the most famous exemplars for design, manufacture, and having an international reputation for performance and quality was the Babcock Boiler. It also became an international standard for marine service, and was exported across the globe. In terms of changes in materials and construction methods, up to that point, most pressure systems were formed from steel plate, formed in semicircular presses and riveted. And the Paxman economic boiler was one of those devices. It was a highly efficient, large horizontal shell boiler. The economic boiler incorporated smoke tubes, which provided a much larger internal heating surface area than equivalent sizes of the Cornish and Lancashire types of the previous generation. At that time, riveting started to give way to arc welding. Joint integrity and efficiency became important in design and inspection, but inspection was limited only in use through hammer testing to check for defects, and only really sensitive enough to pick up large volumetric defects at that. The history of arc welding is of great importance to the pressure systems industry, but not properly covered in this webinar. Now, although joint efficiency has its roots in riveting pattern design, it's interesting to note that the concept of joint efficiency for welded pressure systems remains in some modern codes even today. It's used as a mean to assure safety in place of undertaking 100% NDT and inspection. With the growth and adoption of boilers for electricity and heat provision in the industrial and domestic use, the rise of failures and boiler explosions was inevitable. The Grover Shoe Factory in Brockton, Massachusetts proved a significant turning point in the timeline of the pressure system safety. Although it had a new boiler installed, the factory undertook regular cleaning and maintenance, and therefore an old backup boiler was brought back into service and started up in a cold, damp morning in March 1905. It blew up a short time thereafter. Additionally, barrels of naphtha were stored in a wooden shed directly behind the boiler house, and it was set on fire by the burning coals, and the naphtha exploded, throwing sheets of flame onto the wreckage and driving rescuers away. Between 300 and 400 workers were in the factory at the time of the explosion. Some 117 were injured and 58 died. The yellow line on the right-hand side of the slide shows the trajectory of the boiler. The boiler ended up being lodged in the home of an adjacent neighbour, and this gave great concern to the governor of Massachusetts, who was concerned about having an industrial plant in residential areas. Now, the backup boiler had been inspected in December, just a few months earlier, and found to be in good condition. The boiler inspectors who examined the ripped open boiler reported finding a crack in one of its riveted lap-jointed seams. Experts characterized the boiler, built in the 1890s, as old technology, likely to have a short service life under high pressure. And at the time, there were thousands of similar boilers in use in the US. Engineers estimated the force of the boiler explosion as equal to 660 pounds, that's 300 kilograms, of dynamite. Now, as such, the American Society of Mechanical Engineers had been founded in 1880 in response to boiler explosions that had become common as the use of steam power expanded during the Industrial Revolution. And by 1890, some 100,000 boilers were in service, and many of them unsafe. Inspections were rare, and operating guidelines were almost non-existent. And following the Brockton incident, the governor of Massachusetts acted. A board of boiler rules was formed, and having established the boiler test code in 1884, ASME then formed a boiler code committee in 1911 that led to the Boiler and Pressure Vessel Code being published in 1914. Now, regrettably, this was not the last boiler explosion that Massachusetts was to see. In 1962, the New York Telephone Company had a boiler which again was brought up to service, and it exploded at lunchtime, killing 21 people and injuring 95. A city agency later determined that the boiler had been improperly maintained and operated. Now, this slide shows the development of standards in the US. So it covers quite a large time period, but it's important to note that from that 1914 first edition, there was constant development of the ASME Boiler and Pressure Vessel Code to 13 parts, with some major milestones being the ASME 3 Nuclear Code in 1963, including a design by analysis section, ASME 8 Division 2 Alternative Rules in 1968, and ASME 8 Division 3, the High Pressure Code above 10,000 psi in 1997. It's also interesting to remember that ASME is a not-for-profit organisation which writes standards and works as an accreditation body and entitles third parties to inspect and ensure compliance with the Boiler and Pressure Vessel Code. Now, the story is different in the UK. It's similar, but government-driven. So back in 1817, the government set up a select committee under the title to consider means of preventing mischief of explosion in steamboats to the danger or destruction of His Majesty's subjects. I quite like that language, but it reminds us that at the time, there were no bridges across the River Thames, and the only way to get across the river was to use these penny steamboats, often blowing up. And unfortunately, in Victorian times, people used to go down to the riverside to look at the macabre bodies being drawn from the river. In 1883, the Factory Act became law and inspectors were appointed. And then, harking back to Fairburn, the Manchester Steam Users Association was formed to disseminate information about boiler explosions. BSI, the British Standards Institution, was formed in 1901 with further development of rules and procedures. And these are the milestones for the pressure vessel code in the UK. Firstly, with 1500 as a fusion welded pressure vessel code for use in chemical, petroleum and allied industries. And then the general development for a universal unfired fusion welded pressure vessel code, BS 1515 in 1965 with higher design stresses. And then Roy Nichols' report suggesting that there should be one pressure vessel committee for all equipment in all industries. And as a result, in 1976, BS 5500 was published, becoming the master pressure vessel standard. And there's a copy of the original 1976 code. And then the final and most recent incorporation would be PD 5500, which became PD 5500 in the year 2000 and is still being worked upon even today. And during the last 45 years, there has been continual development of BS 5500 and then ultimately PD 5500, with this being the responsibility of two code committees, the Strategy and Policy Group PV1 and the Design Methods Committee PV115. The code has seen lots of improvements and refinements of methods, adoption of new methods, especially from Europe, when the fall of the Berlin Wall revealed a different culture and different methods which were adopted into the European code and then into PD 5500. A significant milestone would be the development of computer software for BS 5500 and eventually IMechE. And this has been available since the 1970s and early 80s, originally through a dial-up system to a mainframe server, and then ultimately through software tools like Fingo, which was the first to be based on a desktop PC. Now, a PDF version of the code has been available since 2000, and of course, training courses are continuously being run under the auspices of the IMechE Pressure Systems Group. It was also a pioneering document in the UK because it also allowed design by analysis rules, allowing the use of finite element analysis. And that's the version of the code today. Now, it is worth reminding ourselves that this is not a British standard, it's a published document. And this was because of, at the time, the UK being part of the European market, and therefore barriers, the PED was brought in to remove barriers to trade and to allow harmonized standards to operate across Europe. Now, let's think about some major milestones in terms of failure. The major failure in the UK, certainly in my lifetime, was at Flixborough. Flixborough was a chemical plant close to the village of Flixborough in North Lincolnshire, with some 28 deaths and 36 of the 72 people on site seriously injured. Now, this would have been much higher had the explosion occurred on a weekday, but it fell on Saturday, the 1st of June, 1974. At the time, there had been a hasty equipment modification, and the mechanical engineering issues were overlooked by the managers at the time. Indeed, there were no mechanical engineers on site. It was mainly staffed by chemical engineers, and the severity and the consequences of failure were not taken into account. It led to, and is often quoted in the justification of, a more systematic approach to process safety in UK process industries. And the Health and Safety at Work Act was published later that year. It was in train, but it really sharpened the focus on that activity. There were several other incidents in the 1970s which also led to safety system changes. The Seveso disaster, a chemical plant in North Milan, Italy in 1976, led to exposure of dangerous TCDD chemicals to a population residential populations and led to standardized industry safety regulations, including the Seveso III Directive, now the European Directive 2012/18/EU. It's important to note the contribution of safety through legislation and good practice. And these are some of the important EU, typing error there, directives and UK legislation highlights. The COMA rules, for example, the Pressure System Safety Regulations 2000, although they're not applicable offshore, and the Pressure Equipment Directive. Now remember, the Pressure Equipment Directive originally was published in 1997, and it's a directive from the European Community to member nation states, and it was implemented in the Pressure Equipment Safety Regulations. Now, since the UK has withdrawn from EU, these have been changed and amended, and now we have the PSMR regulations and the Pressure Vessel Amendment regulations for Northern Ireland. The PED is significant because at the time, this was the first set of standards for design and the first directive, setting out, as it were, standards for design and fabrication of pressure equipment. It also set in place administrative procedures for the conformity assessment of pressure equipment across the harmonized market for the free placing on the European market without any local legislative barriers. It contains essential safety requirements and how they were to be met by inspection and quality of manufacture. Also, it provided some hard numbers, some safety factors, which were previously contained to design codes. And it has been mandatory throughout the EU since May 2002. Now, the British standard for pressure vessels isn't PD 5500, rather it's BSEN 13445. It still is called the European Code, but it is indeed the current British standard. And it automatically provides presumption of conformity. It was 9 years in preparation and first published in 2002. The safety factors were copied from the PED and now cannot be easily changed. It is a similar format to the UK code PD 5500, and we find that within the PD 5500 committee community, we find it easier to make changes in PD 5500 rather than having to go through the European administrative process to make changes through that route. Originally, it was published in 10 parts, but it's now growing in coverage. And a new edition was published in 2014, and the latest version came out just a year or so ago in 2021. Now, design is one way of assuring safety, but assuring safety also comes through inspection, assessment, maintenance, and even more modern approaches such as risk-based inspection. And here we're trying to ensure a robust system for assuring structural integrity of our system. It also depends on inspection and detection, the various NDT approaches that can be used, from visual, eddy current, magnetic flux, MPI, dye penetrant for surface defects, and radiography and ultrasonics for volumetric detection. It's a powerful tool for life extension on pressure equipment, and that's a really important aspect for the pressure systems group in the UK, as we have a number of significantly aging assets in the UK asset base. It has also given rise to defect assessment codes such as BS 7910 and API 579. And also there are a number of companies who specialize in providing asset life management systems and a holistic assessment system. Now, inspection has come significantly forward since the days of hammer testing. And here's a photograph of an old X-ray machine at Babcock's in the late 1950s, which was used to assure safety in the then new nuclear program. Inspection techniques have come on leaps and bounds in those days, and it's a constantly improving field, which the pressure systems community needs to take awareness of. Portable X-ray and ultrasonic testing equipment, phased array, ultrasonic testing, and time of flight diffraction are just some of the new techniques that have come to light in recent years. There is, however, a drive towards automation with higher resolutions, digital imaging, faster response times, and even using machine learning and AI to help diagnose the outputs from these systems. Indeed, at this particular time, there is a new project looking at automated welding equipment inspection and monitoring, the AWESOME program, which is sponsored by Babcock International, Cavendish Nuclear, AMRC at Sheffield, and the ANRC at Strathclyde. And this is looking at the development of an integrated package of machine learning, sensor technology, and advanced remote manufacturing processes to deliver welding, weld inspection, and potentially weld certification all in real time. And I know the Pressure Systems Group will be looking to that in one of its future seminars. Now, what are the future challenges for the pressure systems community? Well, new nuclear build. The UK has had a strong and proud heritage in nuclear build since the late 1950s and early 60s. With Calder Hall through to Sizewell B, the UK has had 9 nuclear stations. And indeed, just after the last reactor was completed, 1997 saw just over a quarter of the UK's electricity generated from nuclear. It's highly successful, but politics, privatization, and the Chernobyl event halted investment, and there really has been no new activity or new build for 20 years. But Hinkley Point C is well underway, and Sizewell C is in the mix in the future. And here are some pictures just to show you where Hinkley Point C is at this summer, with a commissioning date anticipated to be June 2027, with a 60-year life. And the upper right-hand picture shows the main nuclear island site, with a hole where the reactor vessel, which is shown in the lower right-hand side, will eventually go through and be installed. Other future challenges to the community would be that of reducing oil and gas usage. Now, the UK has benefited from North Sea oil since the 1970s. It's been a major contributor to the UK energy base, and in 2021, 43% of our gas and 32% of our oil were supplied from that source. However, it's an aging asset, both the structural aspects and the geological aspects, and significantly more challenging environments going forward. Just going back to some of our earlier comments, the offshore legislation is different there and a much more challenging environment. But many new technologies and materials were developed for the offshore sector, including new fatigue rules for welded structures. And these were developed through work with TWI and have been embedded into most modern pressure vessel codes. Other issues for the pressure vessel community would be addressing net zero. And there's an appetite at the moment for exploring the hydrogen economy. Now, at the time of writing, there's no settled approach. There may be a vision to create energy from offshore wind, to use electrolyzers to create hydrogen, which must be stored and then distributed. It's at a very high pressure, and there are major storage issues. There are conversion issues. Could we make it into ammonia and store it through that route? There are carbon fiable type 4 vessels already in existence. What about metallics and H2 embrittlement? What about leakage? Hydrogen, the molecular aspects of hydrogen make it prone to leaking through bolted flange joints, and wider transportation. And if this is something of interest to you, then I would point you towards the future of hydrogen. The International Energy Agency presented a report for the G20 in Japan in 2019, and an excellent report by the Henry Royce Institute in Manchester called Materials for End-to-End Hydrogen. Pressure systems are also involved in solar power. And here is one of the Senner thermal-solar power plants. These tend to be based in warmer climates than the UK. This is taken from a plant in southern Spain, and they have these all along the north of the African coastline as well. The idea here is that we have a tall column of molten sodium heated to a temperature of 565 degrees, which then goes through a cycle of heat exchange to ultimately create steam, which can then be turned into electricity through a turbine and in the usual manner. One of the issues with these is you need a large mass of land, and at the moment they are only able to cope with typically 20 megawatts. for a plant of this size. So it's a significant investment for a limited amount of energy capacity. And this would be comparable to the largest offshore wind turbines, which are currently approaching 12 to 15 megawatts, and with a future ambition to go to 20 megawatts themselves. Again, addressing net zero, there is a significant discussion around the development of small modular reactors. Again, at the time of writing, no settled approach, with over 50 current designs presently available. These systems would be capable of producing 300 megawatts and typically refueling in year 6 or 7. So they could be a very attractive proposition for distributed networks. There are also designs for very small modular reactors with microreactors up to 5 megawatts, which could be used for transportation systems and trains. And this is currently receiving much political attention. Another area of interest for the pressure systems community is sustainability and carbon recycling. And a plant which converts CO2 to methanol was opened just last month in China. The Xunli plant in Henan province uses an emissions to liquids technology, which basically involves using special catalysts to convert carbon and hydrogen feeds into low carbon intensity methanol. Now, compared with regular approaches to producing methanol, this will save 500,000 tons of CO2 per annum compared with that traditional approach. A very interesting technology and one to watch for the future. Now, finally, with regards to manufacture, the additive manufacturing process, again, has seen much attention in the pressure systems community, with the pressure systems group running a seminar just last year. Wire arc additive manufacture is one technology which allows us to build large-scale components. It's a flexible manufacturing, and material is made as the component is deposited. Now, there are issues around repeatability, inspection, and certification, along with material properties. Digital IP issues could also be significant because you design these using a CAD model, a slicing program, a robot, and then a deposition head. And it's quite easy to imagine these digital models being stolen, and unscrupulous users could then build their own components in other parts of the world. However, additive manufacture does allow the potential for novel shapes that cannot be made through conventional manufacturing to be considered. And indeed, there is a new draft EN 13445 code, part 14, now available for comment. So as we bring our talk to a close, pressure systems has been at the heart of global industrial growth for over 175 years. It has a proud past. Mechanical engineers have developed technologies, procedures, and practices to ensure safe designs and working practices. Pressure systems is a core technology which is integral to addressing many of the grand challenges, addressing energy provision, sustainability, and carbon reduction as we move to net zero. And it's essential that we learn the lessons of the past and encourage, train, and inspire the next generation of pressure systems engineers. And only then will we have a truly proud past and an exciting future. And thank you for your time this afternoon. Thank you.
Well, thank you very much, David, for a very interesting review of the history as well as a look to the future. That was really great, and also very well timed, exactly to the agenda. So we've had a couple of questions come in, which we'll look to answer now. And for those who perhaps haven't asked a question but have one, please post that, and we'll try and answer it in the remaining time. So the first question I'd like to address is one that says, why do we have different codes between ASME UK and Europe when the technical aspects should not be different? Surely mixing codes causes confusions. If it's just the commercial rationale, separate that out. So that's quite an interesting question in a number of parts. So I suppose the first thing I would like to say on that is that one of the things you don't do is mix codes. That's very much a taboo in the design community. Now, why do we have different codes, or why do the Americans have a different code to the UK? Well, they're basically quite fundamentally different, and at a very simplistic level, the Americans accept lower design stresses but do much less non-destructive testing. So if you like, they're accepting you may get more defects in the vessel, and hence you have lower design stresses. So they have that approach. In the UK and Europe, we do more non-destructive testing to make sure our vessels haven't got defects, and therefore we're comfortable with using higher stresses. Some other things around materials. Unsurprisingly, the materials that we have in the UK, the BS 1501s, for example, a somewhat different composition to the American materials, and also for that matter, European materials are different. So we have to have a design approach that takes account of the materials that are available local to where you obviously operate. Now, obviously, in an ideal world, we would all have the same codes, and certainly from a design point of view, the answers are basically the same.
Paul, again, looking back and looking forward, in the nuclear time round about the mid-60s, two things were quite significant about building community. So in America, ASME developed their PVP conference in 1966. England were doing other good things in 1966 around football, but in 1966, the first PVP conference happened. But it was very American focused, and people like Roy Nichols and others developed the first international conference in pressure vessel technology in Delft in 1969, and it runs roughly in a 3 to 4 year cycle, because it was felt there was an appetite for an international ISO standard for pressure vessel design. And there was a tentative draft at that in 1973, but there was an energy crisis going on at the time, and when there are times of challenge, then people hunker down to what they know, and it kind of died because of politics and competitive markets. So I totally accept the comment and the question that if you're a piece of steel or a piece of steel in a vessel or a pipe, you're under stress, you want to fail, you want to yield, you want to crack, and it doesn't matter which code you're just going to change your shape, or you're going to crack, or you're going to degrade. So I very much, as an academic, would love to see a universal code. And again, knowing the politics of the system, the Americans will love it to be their code. But it's for the next generation to work together. We through other world events have seen the benefit of collaboration, and I can only say it's a good thing to do so. We've learned so much from Eastern Europe in the last 20, 30 years after the fall of the Berlin Wall. New methods, new approaches. So I'm all about inclusion, but we are stuck as an industry with our own particular politics and history.
Yeah, and it will require some quite significant changes, particularly on the materials front, where each country has its own material standards. And for the Americans and us, we've got to sort out this: do we go for a high stress code? And when we say high stress, is basically 2/3 of yield, don't we? And they limit their stresses to UTS over 3.5.
Yeah, the whole world has UTS. The whole world has 2/3 of yield, and there's a variation from UTS over 3 up to UTS over 1.875 if you use design by analysis. So users just have to be extremely aware of what they're doing and what the context of their service requirements are. Good question.
Yeah, good question. So we'll assume that one's satisfactorily answered. So the next one is one that I'm less confident to answer, and that's why are new nuclear civil plants bringing impact on pressure systems? What's changed against previous plants? So my first observations to that are, obviously it's some time since we built the last plant. You know, we were talking about Sizewell being 30 years ago, and obviously there have been substantial changes since then, both in better manufacturing techniques and the ability to detect defects, which we need to take account of. And another observation is obviously that the expected life, the stations at the time were expected to last 30 years, 250,000 hours. Now we're looking at 60 years, which is double the length of life. So we have to look at what sort of defects we can tolerate. You know, can we tolerate the same size of defects, and can we detect these smaller defects? We've got different materials. We've got a more international manufacturing situation. As I understand it, a lot of the components are now being made in Japan, whereas previously they're made in this country. So there's some quite substantial differences. And I'm sure David knows a lot more than I do, having been closer to nuclear.
Well, one of the things that I've got to say is that we don't really cover a lot of nuclear activity within the Pressure Systems Group, although our current chairman, Dr. Paul Smith, is our nuclear expert, as it were. And the questioner is absolutely right in their assessment that much of the technology that we see today, especially in Hinkley C, in terms of the pressure system, is I don't want to use old, but it's evolved a little, but it's not significantly different from the reactor technology that has been used over the last 20, 25 years by EDF. So the point is well taken. I think for me, one of the challenges is not, if you like, a design or strength of materials or manufacturing consideration. It's actually people. And you highlighted that, Paul, in the 60s, 70s, and 80s, the UK really had a world-class team. The CEGB, people working down in Gloucestershire at the CEGB research labs there, have made a phenomenal contribution. But unfortunately, through the 80s, much of that was sold off or wasn't felt to be of great value, and people retired and weren't replaced because the new nuclear build program was not happening in the UK. So I think we've got a hill to climb. It is a challenge, but it's an ambitious challenge, and I do think it's exciting for young people to be involved in new nuclear build and hopefully SMRs in the years ahead.
That's very good. Right, well, we're getting quite a few questions coming in, so I'm just going through some of them. The next one was the third question to come in, and that was an interesting one, really. It's not particularly pressure systems related, but it was looking at that thermo solar power station and saying, what's the advantages over solar cells? Why not use solar cells instead? And to be honest, I've got no answer for that, David, but I just wondered if you...
Well, it's not a word I'm super familiar. I actually got involved at one time on design of the supports of some of these large-scale towers, which expand and contract every day. So there is an issue about ensuring that the expansion and contraction happens and is not restrained in any way, shape, or form. And secondly, there's a significant fatigue issue with the cycling at fairly large swings of temperature over time. But as I said in the presentation, they're limited capacity. And in fact, the real, I suppose, the real fruit of solar power is using PV. And in fact, speaking to some colleagues at the university that's their world of energy systems, tell me that in China at the moment, they're putting in 20 gigawatts of solar PV. So it's an interesting technology, as are other types of solar cells. But at the moment, the significant gains are coming from solar PV.
Okay, thank you. Next question. Is there an exact definition of what a pressure system comprises in terms of equipment used and maximum pressure experienced? Well, if you go into the regulations, the PSSR or the PR, they've both got definitions of when they apply, and both of them only start at half a bar. So any pressure systems below half a bar aren't considered at all in the regulations other than pure. So in terms of what it comprises. Well, the pressure system safety regulations talk about a system comprising a vessel and its associated pipework and release streams. But to be honest, I think the answer to this is there an exact one? No, really. Beyond that.
No, there isn't. Most codes and standards actually tell you what a pressure vessel is not, or they will point you towards a special code where you can have, simple pressure vessels or refrigeration vessels and so on. So the short answer is there's no unified, precise definition. But you kind of know one when you see one if you've been doing it for a while. And as I said earlier, it's always good to get some training.
Okay, next question. Just mindful of the time. Please speak a little about placing vessels designed to ASME 8 into service in the EU. What are the key supplementary requirements for the designer manufacturers to be aware of in terms of regulatory compliance? Well, two things. First of all, if you've got an ASME vessel that was placed on the market in America or some other country that isn't in the European Union, and it's brought into the UK, it has to comply with the pressure equipment regulations because it's been placed on the market there for the first time. And that is pretty tricky, really. Second part, if you design a vessel to ASME, and some people choose to do that, particularly the oil industry, then there are documents produced that breach the gap between what ASME covers and what the PER requires. But it's principally associated material properties, really, and test pressures. David, anything to add to that?
Yeah, well, the question is actually universal. It's how do you place any vessel from any code, ASME or otherwise. If you're Chinese, it's GB 150, Australian, it's AS 1210, or in fact, even using PD 5500, the onus is on the manufacturer to demonstrate that they have met the essential safety requirements. And as you know, Paul, you've mentioned about material strength and integrity. It also looks at the hazard and risk, which are two quite topical comments about the hazard and the risk of it happening. And then going through the looking at this in terms of pressure and volume, we end up with a conformity assessment procedure, which then tells the manufacturer how and when and what to inspect and what the intervals should be and what the rigor of inspection should be, depending on the severity of the conformity module that's adopted. So the procedure is the same, whether you're ASME or now UK or any other international country placing things into the European market. You just have to comply with the PED and the essential safety requirements.
Just one further thought on that. All the responsibilities in the pressure equipment safety regulations lie with the vendor. So basically, it's his job to sort it out, really.
Or hers.
Or hers, yes. Well, their job sorting out. Yeah, sorry about that. Right. Let's have a look at this one. There's one for you, David. Why did you consider it necessary to join ASME? Some countries not recognise chartership from the IMechE. No, I don't think that's at all.
No, I was very much involved as a student member of the IMechE. I hate to say in the 1970s, and then when I graduated, I became an associate member as soon as I could, actually, because for me, I had an appetite for learning. I went to work in industry, and then I was no laughing from our younger delegates in the webinar today. I was the last graduate to go through Strathclyde without PCs, and I just thought this is the way forward. So I did a part-time master's degree, and then was introduced to sort of research. And at the time in the UK in the early 80s, there were no research conferences in the world of pressure systems, but there was an annual ASME conference. So I went to that a few times, and I thought this is a really interesting community. They gave you a monthly newsletter, sent out research papers, had the Journal of Pressure Vessel Technology. So I joined ASME. And then over the years, probably 20 years later, I was nominated to become a fellow, which was it's a great honor, actually. There's not very many UK-based fellows of ASME. But it's about building, for me, a robust network, both at home and overseas. And similarly, I've got some very good colleagues in Asia and especially in China who I've known for a similar 35-year period. So nothing to do with accreditation or recognition, more a case of me wanting to learn and to be aware of what's happening worldwide. And the American research community and codes development community were going at pace at the time. So good question.
Okay, another interesting question. Can you give a good example of Eastern European different thinking post the fall of the Berlin Wall? Well, I would say flange design is the obvious.
Absolutely. Yes.
The European method of flange design is far superior to the British one, which goes back to the 1920s. And in particular, it looks at fugitive emissions, and you can take that into account in flange design. Obviously, for a higher integrity flange, you need a better seal, and you don't want the product leaking out. So, yeah, that was a good example. David, any other examples?
No, that's the big one, because the methods from Europe allowed us to do flanges with dissimilar joints. So you could have a heat exchanger flange on one side, a tube sheet, and a different pressured heat exchanger flange on the other side. And the method allows you to do that. It also includes thermal effects as well as sort of structural effects. We adopted the rules for cones in the British Code, and we adopted the rules for local loads and for saddle supports. So there are a whole raft of approaches based principally on limit analysis, which we used much more a stress-based approach in the UK, but also just culturally to meet colleagues from Germany at the time was really exciting, just to listen. And I'm sure there was similar interest from them to us to them, sorry. But the ambition at the time, of course, was to grow the European standard EN 13445. So lots went in, and unfortunately some things went out. But we still have some of those back in PD 5500 if required.
Right, thank you. Well, with the time as it is, I'll just take one last question, and that's quite an interesting one. What is the current status re the Brexit position on pressure standards? Now, I suppose my simple answer to that is basically nothing's changed. As far as Brexit's concerned, we've renamed some things, and the approach isn't really any different in the future. We don't know. We've got the opportunity to move away, but for now, it's pretty much the same. You can find that out, obviously, by various positions, papers and so on. The other thing is, I suppose, British standards are still a member of CEN, the Central European Standards Body, and have no intention of leaving it, to my knowledge. So anything to add, David?
No, you're absolutely right, Paul. There are several countries that are not part of the European community, but are members of CEN, and we will retain our status, and we participate in CEN TC54, and Working Group 53 is a design methods group that myself and Simon Erland and others go to. So no, our sleeves are rolled up and we're participating, but we still, for the time being anyway, plan to continue developing PD 5500 and EN 13445.
That's great. Well, with that, the time's at 1 o'clock, so I'd like to thank David very much for his presentation, and note that he prepared that in his spare time and had some difficulties along the way with his computer and his internet access to cope with, which were quite significant. So I'd also like to thank everyone who came today for attending. It's been a really good turnout, and I hope everyone's enjoyed it. I apologise to anyone who's posted a question, has had it answered yet. I'll have a quick look through those, and I'll see if I can find a way of sort of getting back to anyone with an answer. So thanks to everyone again for joining, and I hope you enjoy the rest of your day. So goodbye from me and goodbye from David, as they say.
Thank you.